In this video, I'll talk about the chi-square test for goodness of fit. And that test has two opposing hypotheses, just like any hypothesis test. It has opposing hypotheses, but they're in words, they aren't symbols, because this is a non-parametric test, meaning we're not trying to guess about a parameter like a mean, mu, or a proportion, pi or p. So the null hypothesis is that the population fits the given distribution, and I'll talk about that in just a second. And the alternative hypothesis is that the population does not fit the given distribution. So what is the given distribution? Well, that depends on the problem. And so I've just put in a sample problem here, and I'm just going to talk you through it. So let's say that there are three different study areas in a school. And you've got 99 students. And if they were going at random to these three different study areas, then you would expect to have about a third of them in math, a third of them in the science study area, and a third of them in the English study area. However, what you observe is 25, 24, and 50 in the respective study areas. Now, what I said about the given distribution, you don't have to set this to be totally random. You could say, well, the given distribution that I'm guessing is 25%, 25%, and 50%. But this one, the way I have it set up here, is expected value would just be the totally random case. So every student has an equal chance of being in any one study area. So these numbers are set, the expected numbers are set before you actually make the observations. Okay, then we put in the observations, and I've made a little sheet here just to walk you through what the goodness of fit test does. There are plenty of different software packages that'll do this for you, so I just gave you a general one so that you could then apply this knowledge to any software package that you see. But this is what you're understanding, is the observed versus the expected numbers. Now, if you were doing this by hand, you would then, for each one of these rows, you would calculate the observed minus the expected number, and then square that. So 25 minus 33, and then square that number, and then divide that by the expected number, divided by 33 in this example. And you'll do that for every single one of the rows. Then, to calculate the p-value, I'll go to three categories. I have this set up very generally, so I'll go to three categories because we have three categories. And let me double click on this. First, let's note that we have three categories. So this number 3 here, this cell will be called, but it'll be covered up when I double click on this. Okay, if you want to do it by hand, you've got these numbers, then you can use the chidist function in Excel. And that'll give you the p-value. It'll give you that area under the right-hand tail of the chi distribution. So what are you taking the finding the value of? Well, it's the sum of these numbers that we just found with the degrees of freedom, the number of categories minus 1. So that's why I pointed out that was 3 there. So I'm calling cell D20 in column D, row 20. And that's the number 3. So 3 minus 1, so 2 degrees of freedom. And that's really the basics of the chi distribution function in Excel. But what it gives you is then the p-value right there. So this is the p-value, 0.001. Well, just like any other hypothesis test, a very low p-value means that we reject the null. And that is a very low p-value. A lot of times you're going to be comparing it to some alpha of 0.05. That is a significance level of 0.05. But this is, regardless, this is a low p-value, so we will reject the null hypothesis. Then the conclusion, if we are rejecting this null hypothesis, that means that we're kind of saying yes to the alternative or the alternate hypothesis. We never say accept, but we can say that evidence suggests The evidence that we have suggests that the population does not fit the given distribution. So in other words, what we have here are observed numbers of students, and at first glance it looks like no way does it fit this, because you've got 50 people going to English and only 25 and 24 going to math and science. But we do a formal hypothesis test, and then we say, look, it looks like, from what we see, it looks like even if we had the data on all the population, all of the students that ever will or ever have been in this scenario at this particular school, they would disproportionately choose English over the math and science. And so that's what we're saying there by rejecting the null. The population does not fit this given distribution that we have supposed. So there is a first look at the chi-square test for goodness of fit.